this along the vertical axis versus E this way. And similarly, you draw a second graph again, you have E along the horizontal axis, and your vertical axis now would be this. Okay, for a given value of E. Now, where these two graphs cut, where they intersect, that will give you a value of E that is allowed. In other words, when the left-hand side equals the right-hand side. I hope you followed that logic. Okay, if not, rewind. Okay, so both, well, I'll try and summarize a little bit. These two expressions, left-hand side and the right-hand side, both of them are functions of the energy of E. Okay, so draw two graphs. So in one graph, let's say for both of them, the horizontal axis is your energy, your E, which can vary, right? And the vertical axis would be, for one graph, would be this. You find, you know what, for a given value of E, you plug it into the alpha and you find out what cotangent of alpha A is, and you plot the value. So you get a graph for the left-hand side. And similarly, beta over alpha is a function of the energy E also. Okay, so you can draw a graph of that one as well. And where the two graphs cut, right, where they meet, where they intersect, that will give you a value of the energy E such that the left-hand side equals the right-hand side, right? And that energy value where they cut, that is an allowed energy because the left-hand side equals the right-hand side, which is what a restriction we must have, given the restrictions we placed on ourselves for the wave function, the single valued, continuous, normalizable, blah blah blah. All right? Okay. Now, to actually find, to draw these graphs is tedious. You'll need a computer. You'd need a computer to do that. So you'd have to solve them numerically, using a computer. Now, that's just what I've been saying. Well, here I've got the energy as the vertical axis. Well, I mean, you could just do that, right? It doesn't really matter. The point is where the two graphs cut, where they intersect, that will give you the allowed energies, right? Now, this is a bit inconvenient. So the guys who were thinking this up in the first place, they again changed the variables. They translated into a more convenient form, and I'll just mention that briefly. Now, I've run out of board, so I can't give you detailed solutions yet. So, but I'll give you a taste. Right? Okay, so let's transform again, and you'll say, why do you do this? Well, it works, makes things more convenient, but it's not obvious at the beginning. But with hindsight, you'll see why it was done. All right. So I've got three bars here. So definition, right? So let's define gamma now. So you've already got an alpha and a beta. So now we're introducing a third Greek letter term. So let's define gamma as the square root of 2mv naught a squared all over h bar squared, right? The square root of all of that. And that's a constant. So gamma is now a constant because all these terms here are constants. Right? So gamma is a constant. Whereas this x here is just defined to be this constant, gamma, times the square root of e over v naught. Now E is the energy, right? E can change. E is a variable, and therefore X is the variable. X depends on E. X is a function of E, right? Now, given these two things, so if you then divide gamma by X and square the result, and then subtract 1, and then square root the whole thing, you will. It's just algebra, right? Nothing physics. It's just simple algebra. So do it at home on a pad, pad and pencil or whatever. So if you do that, now you know what gamma is. Here's gamma. You know what x is. That's given, right? So work out what the left-hand side should be, and you will find it's equal to beta over alpha. Now you know what beta and alpha are. Here's your alpha, here's your beta, right? So you know, do the math. It's just you know, the 9th grade algebra or whatever, just you know, high school. So you'll find that this left-hand side, this expression, is equal to beta over alpha. And you may say, well, why are you doing that? Well, because, maybe I'll come back to it. I'll bring it all together. Okay. So this equals beta over alpha, and you can prove that. And this beta over alpha, that's the in effect, you're translating this into something with x in it, right? So instead of using beta over alpha here, you'll start using this because they're equal. All right. Now another little bit of algebra, you can show pretty readily that this x here is actually just alpha a. So do that also as a homework exercise. Okay, x equals alpha a. Now if that's the, and it is the case, so if you then cotangent both sides and then minus, so you will get minus cotangent x, and whatever you do on the left hand side you do on the right hand side, so that has to equal minus cotangent alpha a, right? Here it is here. So minus cotangent, or cot, minus cotangent x is equal to minus cotangent of alpha a. Why? Because x is just equal to alpha a, right? From here. Okay, now we can bring it all together. What have we done and why have we done this? Well, we've got here now beta over alpha is this expression with x in it, right? And we have minus cotangent of alpha a. So bring this minus over. So I've got minus cotangent of alpha a is minus cotangent of x. Okay? So instead of this equals that, we translate the problem, and now we can talk about, let's see, minus cotangent of alpha a, bring this minus over here. So for here we can substitute this by cotan of x, right? So we've sort of got cotan of x on this side, and on the right hand side we've got this expression, so beta over alpha. We've got this square root thing. Okay. Now this square root thing, this here, and cot x, both of them involve x and only x. Both of them are now expressions of x, right? So it's more convenient to work with your x than your, well, these where your alphas and betas, they're functions of the energy. Whereas here now we've just got two expressions that are functions of x. And what is x? Well, it's just an angle, right? So we're talking about angles. So instead of drawing graphs like this, which is a pain, we've simplified it a lot, and now we can draw two graphs using x, say along the horizontal axis, and we draw one graph that maps this value here for x. So this vertical axis here is this square root expression, square root of gamma over x all squared minus 1, right? So we for different values of gamma, like here's a graph, a curve for gamma equal to 1. Here's another one for gamma equal to 2, and here's one for gamma equal to 5, and so forth. So we get different curves, obviously, for different values of gamma. Now what's gamma again? It's this. Okay? And so it looks as though you're treating gamma actually as a variable. So what are we varying? I guess the size of your A, I suppose, right? Assume, or are we changing V? Oh, well, maybe both. Anyway, so for different values of gamma, you'll get different curves. Okay, along the for x this way. Now the second curve, you've got minus cot x. Now you need to go. There's a bit of revision again. This beta over alpha, that's this square root expression, right? And this cot alpha a, that's cot x, right? So perhaps I should have written it down. Anyway, you're translating this, which is both of these left and right hand sides, they're functions of the energy E, and you're translating that problem into so you have this on the left hand side and cot x on the right hand side. So instead of well, the other way around, instead of having beta over alpha here, you can have this square root expression, and instead of having cot alpha a here, you can have cot x. Okay, so if we draw now the graphs for x, now it's just the cotangent, well, minus the cotangent of x. That's easily done. Right? We know about how to draw graphs for cotangent of x. It takes these values, and the cotangent or minus cotangent takes as x approaches pi or 2 pi, this becomes infinite, so it screams up. It asymptotes to the value of x as pi and 2 pi. Okay, now I've run out of board, but if